All right, let's get started with Chapter 8. And so the first section in Chapter 8 is exploring exponential models. Chapter 8 is going to be all about graphing exponents and graphing exponential functions and models. So, lesson preview, what we're going to learn, we're going to model exponential growth, and then we're going to model exponential decay. So the vocab for the section, exponential function, growth factor, decay factor, and then asymptote. So we'll be on the lookout for those vocab phrases as we go through. But first things first, let's get our skills check going. So we need to be able to plug numbers into variables and see what they evaluate to. So number one, I'll do, you're responsible for the rest. 2 to the x, and we're going to plug 3 in, so it's 2 cubed, and 2 times 2 times 2 is 8. Alright, so pause the video, knock out 2 through 6, and when you're ready, press play, and we'll get going again. Okay, so what is an exponential growth model? So sometimes you're going to have data that starts off slow, and it kind of grows, and then at a certain point, it takes off. It gets really big, really fast. Okay, so population kind of grows like this sometimes. Cell growth, if you're doing a science class, will grow like this in a lot of cases. Money growth, if you're getting interest, can grow like this. So anytime you have a graph like this where it's flat, 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 and then takes off, it's going to be modeled by this function. The general form is y equals a times b to the x. Okay, so we're going to need a number for a number for b, and then the exponent is going to be a variable. Okay? All right, you can use an exponential model to model growth, and growth is where it's flat and then takes off. If b is bigger than 1, all right, so we can't have fractions here. Okay? When b is bigger than 1, b is the growth factor. All right, so the growth factor is how fast we're growing. All right, so let's graph this on our own. So what I want you to be able to do on these problems is do a t-table, and the numbers I want you to plug in for x are going to be -3 to +3. Alright, so 2 to the -3, that's 1 over 2 cubed, which is 1/8. Alright, 2 to the -2 is 1/4. 2 to the -1 is 1/2, and 2 to the 0 is 1. And just a heads up, anything in the world to the 0 power is 1. So that's going to be really helpful for us. All right, 2 to the first is 2, 2 squared is 4, and 2 to the third power is 8. And we'll go ahead and graph this. So -1, 2, 3, +1, 2, 3, 2, 3, 4, got to go all the way up to 8, 5, 6, 7, 8, and so 1/8 is very low down here. 1/4 also very low. 1/2 starting to get a little higher, and then 0, 1, 1, 2, 2, 4. You can see how it's taking off. 3, 8. If we connect these, it's going to get really big, really fast. Okay. And then one thing that we see here, it's never going to get, on this end, it's never going to get lower than 0, okay? Because anytime we're doing a fraction, so we were doing fractions over here, 1/2, 1/4, 1/8, right? Anytime you have a fraction, that fraction is going to be bigger than 0, as long as we don't put a negative. As long as it's a positive fraction, we'll be above 0. So we'll never cross the x-axis. All right, so your turn. Give me the t-table, and then graph these two, 1a and 1b. Okay, so you can use an exponential function to model population growth if you know the rate of increase, r, and this is some percentage, like 8%, right? So we're going to write that as a decimal. So if r is 8%, we would say instead r is 0.08, and then you would plug in b equals 1 plus that. So our growth factor, remember b is the growth factor, would be 1.08. Okay, so anytime you say we're growing by 8%, you want to use 1.08. If we're growing by 10%, 1.10. All right, so let's use that for example 2. Refer to the graph. So we got our graph here for U.S. population growth. In 1800, there were 5 million people in the U.S. and in 2000 there were 281 people in the US. So you can see that we were flat, 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 and then we're starting to take off really quickly here, exponentially. All right, so find the growth factor first, and then suppose the rate of increase continues, write a function to model it. All right, so find the growth factor. So in here, right there, 1.24, the rate of increase, that's our growth factor. Okay, we've already got that figured out. All right, and so we want to say write a function to model this. So the growth factor is 1.24, and then our function is going to be y equals 1.24 to the x. Right, we're getting exponentially bigger, and we're going to start here. We're going to say 281. Okay? If we're going to start in 2000, okay? So if in 2000 x equals 0, okay? So you need some starting point. If we decided that x was 0 in 1800, then we would rewrite our graph and say y equals 5, the original value, times 1.24 to the x. So growth factor, original value. All right, so see if you can take that information and answer our questions here about the U.S. population's growth. Okay, so let's write an exponential function if we have some values on our graph. So we know, and you don't have to graph this, I'm just going to put it on there so we can visually see it. Here's 2, 2, here's 3, 4, and we want to figure out what is the growth that's going through this. Okay, so we've got y equals ab to the x. So here's how we're going to solve this. We've got 2 different points, so we're going to plug this in twice. First, we're going to say 2 equals ab squared. And then we also know that 4 equals ab to the 3rd power. Okay? All right, so what can we do here? Well, first things first, we can get a by itself on the equation on the left. So we've got 2 over b squared equals a. I'm going to take that and plug that in over here. So now I'm going to say 4 equals, instead of a, I'm going to say 2 over b squared times b cubed, and I'll put that over a 1. And you can see here b squared and b cubed are going to cancel out, and so all of a sudden we're going to have 4 equals 2b, and so b must equal 2. Okay? And so now we're in business. Let's plug this back into our original equations. We can plug it into this one. 2 equals a, but now we know what b is. B is 2 squared, and so let's check this. 2 equals 2 squared is 4, and 2 divided by 4 is a half. So a equals a half, and let's go ahead and check it for our other equation over here. 4 equals 1/2. B is 2 to the 3rd power. All right, let's check it. 4 equals 1/2. 2 cubed is 8. Is half of 8 4? Yes, it is. So it checks out. So a equals a half. B equals 2. All right, so now we can write our actual equation. Y equals 1/2 times 2 to the x. X and y are going to end up being variables. We need to find a number for a and b. All right, so that's as complex as we're going to get in this chapter. This is kind of the hard one. See if you can do this using these 2 sets of values, solve for a and b. All right, if you need to, go back and watch this again, but follow steps, get a and b by themselves, and write the final equation. Okay, so we've talked about exponential growth. Now we're going to look at exponential decay. Exact same as growth, except for we start high and then end up coming down to nothing. So if we talk about things like, you've heard of isotope dating, things like that. So you have a certain amount of some sort of chemical that we're looking at, and it has a half-life So it's dropping down, dropping down, dropping down, and eventually there's not much left, but there's always going to be a little bit left. It'll never disappear entirely. Okay, you may have talked about that in a science class so far. B is less than 1, we're going to have exponential decay. Right? So we're losing value very quickly, and then we flatten out. So let's take a look. Without graphing, can we tell whether this is growth or decay? So we're going to look at our growth factor. Our growth factor is 0.95. All right, that is less than 1. B is less than 1. So if we're less than 1, we're going to be decay. Okay, so that's how you can tell right away. If your growth factor is smaller than 1, decay. If it's bigger than 1, it's exponential growth. All right, so without graphing, tell me whether we've got growth or decay for A, B, and C. All right, so let's talk about our last vocab phrase, an asymptote. An asymptote is a line that you get close to but never crosses. So we've seen this already with the x-axis, something that we get close to but don't cross. All right, and so we'll see that again here. Let's graph this. By graphing it, we're going to do our t-table. -3, -2, -1, 0, 1, 2, 3. And then we'll end up with 1/2 to the -3 is actually 2 cubed, so that's 8. And then 8 times 24, what do we have here? 4 times 8 is 32, 2 times 8 is 16, so 192. All right, so then we've got 24 times 1/2 to the -2 is going to be 4. So 24 times 4, 16. 2 times 4 is 8, so we get 96. And then we've got 24 times 2, which is going to be 48. And then 1/2 to the 0 is 1. And 1 times 24 is 24. Okay. 1/2 to the first is a half, so now we get 12. 1/2 squared is a quarter. A quarter of 4 is 6. And 1/2 to the third is an eighth. An eighth of 24 is 3. So here's our graph here. 1, 2, 3. 1, 2, 3. And we're not even going to make it all the way up. Let's go 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I can make it that high at least. 1 is 12. 2 is 6. 3 is 3. And it's coming down pretty steeply, but pretty quickly this is going to flatten out, and we're never going to cross the x-axis here. We're never going to cross it. So our asymptote is horizontal, y equals 0. We are never going to cross the x-axis, the line y equals 0. So that's our asymptote. All right, quickly I want to make sure we know how to graph using our calculators on this. So let's do the same thing here. Grab your y equals and clear these off. And y equals 24 times, and I'm going to put 1/2 in parentheses. Could just do 0.5 to the x. So x is your variable. Okay. I'm going to do my window here, x min, x max. I'll go -3 to 3. Actually, let me go -5 to 5 so we can see these values. And clearly in our y values, the min is 0. We're never going to go below that. So let me go -10 just so we can see the x-axis. And then I'm going to go way up to 200 here. Because you can see here, 192, we're going to need a lot of vertical increase. And here it comes down. And you'll see it gets close to the x-axis, but never crosses it, right? We never see the line drop down here below the x-axis. All right? And then nicely, right here, if we wanted to, we could do our table with the calculator as well instead of having to do it by hand. So let's set our table. We're going to start at -3, and we're going to count by 1. Right? Start at a -3 and then count it by 1, 1, 1. Let's look at the table. There's our values, 192, 96, 48. Right? It's going to do the work for us. All right, so you're up here. Graph each decay function. You can use the graphing calculator, but please label all your points, right? On your homework, I'm going to be looking for you to label at least 3 points, okay, for your exponential decay and growth graphs. All right, last one, we got a real-world connection. Depreciation is the decline in an item's value, right? So when you buy a car, right, it loses its value pretty quickly, but then it'll flatten off, okay? So the exponential decay graph shows the expected depreciation for a car over 4 years. Estimate the value of the car after 6 years, okay? So on this one, if we're looking at this, let's look at some values here, and I'm going to use on this one, hold on one second. So sorry about that. I wanted to look at the textbook to see which values they used because they're not exact on there, but we can say that when we start at time 0, our car is 20,000. That's clear on the graph. And what I looked at is they guessed in the book that after a year it was at 17,000. So I'll use that as well so we have common numbers with the video and the book. So what we want to look here is how much change do we have going on here, right? So we've changed by $3,000 over, what was the original? The original was 20,000. So if you can find a 1-year change and divide it by the original, you'll find the percentage change, which is negative 0.15. All right, and so we want to find the growth factor. We don't want to use 15% because we're not growing by 15%. We're actually growing by 100 minus the 15. We're actually growing at 85%. So that's going to be our growth factor. That's our B. All right, so we can write our equation, y equals, what's our starting value? 20,000 times 0.85, our growth factor, to the x. All right, so we can use this equation. Let's grab our calculator and change our y equals to that, 20,000 times 0.85 to the x. And I'm just going to go straight to my table, but I'm going to start with 0 instead. And it says after 4 years, I'm sorry, 4 years was shown. After 6 years, my car is going to be worth about $7,543. $7,543. All right, so you're up. See if you can keep going with this. Extend it out. See how much the car is going to be worth after 10 years. And that's it. Any questions, make sure they get answered in class, and good luck with these problems.